Hi everybody, welcome back. So video 7 was Intro to Stoic. Video 8 is Stoic Practice. And this practice is not going to be a homework sheet. This is just going to be some practice in the notes, and then you'll have some questions to do on your own here. I did these as homework sheets because I want you to get in the habit of opening the document and doing the homework. It is crucial in this unit to get the practice. You can have all the notes in the test. You can have all the notes in the world on the test, but if you haven't done the practice, you're not going to understand how to use them in an efficient or an accurate manner. You've got to do the practice. I'm going to work through some practice problems on this page, and then you're going to work through some practice problems in homework as well. Just like all the practice, if at any point you think you've got it, might be a good idea to stop the video, try the problem, and then unpause it and check your work. All right, we're going to start off with kind of some easier kind of entry-level practice questions. Most stoichiometry questions are going to begin with a chemical reaction. And this is going to be a very common chemical reaction. C3H8 plus O2 yields to CO2 and H2O. This is the combustion of methane. Step 1 of all stoichiometry questions is going to be get those mole conversions, get those mole ratios in, or balance the equation. You've got to balance an equation properly if you're going to be able to do the problems in this unit. Now, this is combustion, so you had some tricks for combustion. Step 1 was balance the carbons. 3 on the left, I need 3 on the right. I'll put it in red so it pops out more. Then your hydrogens, 8 on the left, so I need 8 on the right. I already have 2 here, so 4 times 2. Then save your oxygens for last. 3 times 2, I have 6 here, plus 4, I have 10 total. 5 times 2 would give me 10. Anything left empty is a 1. So that's step 1. Balance the equations just like you did in your chemical reactions unit. Step 2, well, that's got to come from the problem. We're going to say a propane tank, which is the C3H8, is filled with 15 moles of propane. So you go to the gas station, you pick it up, and they fill it in moles. How many grams of CO2 will be produced when the whole tank is burned? So a good example of where this gets into real world application. How much CO2, how much of that greenhouse gas is going to be released into the atmosphere by burning this amount of propane? Just like with mole conversions, start with what you know. I know I have 15 moles of propane. And where am I going? Well, I'm going to grams. Moles to grams, I know I need to use my molar mass conversion. Now, the molar mass of CO2, I remember it. Carbon is 12 plus oxygen, 16. 16 times 2, 32, plus 12. CO2 has a molar mass of 44 grams per mole. After you've got your ratios determined, then you can start setting up your problem. Begin with what you know. So find your number. I know I have 15 moles of propane. From moles, I can go to grams. Now, I could get to grams of propane, but my goal is not grams of propane. My goal is to get to CO2. To change from one substance to another is where we're going to use our new skill, is where we're going to use the mole ratios. I'm in moles of C3H8, so that's going to cancel out. From moles of one substance, I can go to moles of any substance using a mole ratio. So from C3H8, I can go to moles of CO2. To figure out a mole to mole, use your, I'm going to put in a different color, use your balanced equation. For every 1 mole of propane used, 3 moles of CO2 are released into the atmosphere. Now, from moles of CO2, I can go to grams of CO2. Moles of CO2 needs to cancel. Grams of CO2 would be left on top. I know that there are 44 grams per every 1 mole of CO2. So the only new step is when you switch between elements, you switch using the mole ratios. 15 times 3 times 44. When that tank is burned, I am going to release 1,980 grams of CO2 into the atmosphere. So that would that's a lot more than any tank is ever going to have, but I would release 1,980 grams into the atmosphere. All we've done is add that mole conversion step. And for this practice sheet, I am going to really focus on pulling that out with a second color so that you understand when we are invoking our balanced equation. Now, with the same balanced equation and molar mass, we could also ask how many molecules of O2 will be used. So now, instead of my goal being grams of CO2, my goal is molecules of O2. Still starts off the same. What do I know? I know that I have 15 moles of the C3H8. And I know that label is going to cancel, so it's going to go to the bottom. This time I want to calculate O2, so from moles of propane, I can go to moles of O2. Moles of O2 is not my end goal, so that's going to need to cancel and drop to the bottom. From moles of O2, I can go to molecules of O2 using Avogadro's number. Moles converting between substances, use the coefficients. 1 for the propane, 5 for the O2. So for every 1 mole of propane used, 5 moles of O2 are used. And 1 mole of any substance will contain 6.02 times 10 to the 23rd. Then plug it into a calculator. 15 times the 5 times 6.02 times 10 to the 23rd. I am going to need to use a whole lot. 4.5 times 10 to the 25th molecules of O2. All we're doing when converting between substances, use the mole ratios or the coefficients that allow us to do that. We're going to do one more. We're going to do another example together, but we're going to switch to a different substance. So we're going to switch to a new chemical reaction, so I wanted to make that clear on the paper. This time we are going to be combining aluminum chloride with calcium metal and producing calcium chloride, and aluminum. Step 1, balance the equation. So aluminum, I've got 1 and 1, that's balanced. Chlorine, I have 3 and 2. 3 and 2 can both multiply to 6. So 3 times 2 is 6, and 2 times 3 is 6. Now, I've got 2 aluminums and 3 calciums. So that was a pretty easy one to balance, but get those coefficients out front. Now, and I'm going to say for this particular chemical reaction, we are going to begin a chemical reaction with 150 grams of aluminum chloride and excess calcium. Now, we don't care a whole lot about this sentence yet, but that'll become important later. I'm just saying, assume aluminum chloride is going to be the reactant that determines how much product that you can make. So we are going to begin with 150 grams of aluminum chloride and excess calcium. And I want to know how much of each product can we expect to make. Same setup, start with what you know. So I know I have 150 grams of aluminum chloride. And you will learn very quickly, you need to get to moles, because moles are the bridge and moles are the way that you can convert between everything. They're kind of the central conversion factor. So from grams of aluminum chloride, go to moles of aluminum chloride. Now, I didn't set it up here. I probably should have this time. Aluminum chloride is 1 aluminum atom. Aluminum has a molar mass of 27, plus 3 chlorine atoms. Chlorine has a mass of 35. Aluminum chloride has an atomic mass of 132. So we'll use that aluminum chloride has an atomic mass of 132 grams per mole. So 1 mole contains 132 grams. From there, I'm at moles, so I can switch to another substance. Now, I want to calculate both products. You can pick which one you do first. I'm just going to we'll go to the calcium chloride first since it's first. So for moles of AlCl3, I can go to moles of CaCl2. Use your conversion factors. So not convert, use your mole ratios. For every 2 moles of aluminum chloride used, 3 moles of calcium chloride will be produced. How much of each product? Let's assume they wanted grams. So from moles of calcium chloride, I can go to grams of calcium chloride. The molar mass of calcium chloride is 111. So there are 111 grams of calcium chloride for 1 mole. Punch that all into a calculator. 150 divide 132. Now this is our first time with kind of a double fraction bar. Treat them like 2 different steps. Times 3, because it's on top, divide 2, because it's on bottom, times 111. And we end up with 189.2, rounding to 2 sig figs, or 190 grams of calcium chloride are going to be produced in this reaction if 150 grams of aluminum chloride are used. Now, we also wanted to calculate the other product. It's going to start off the same. The only thing that's going to be different is that very last step. I'm still going to go from grams of aluminum chloride to moles of aluminum chloride. From moles of aluminum chloride, I can still go to moles of another substance. This time I'm going to go to my other product, which is aluminum. Now, hopefully you didn't copy this right. For every 2 moles of aluminum chloride used, there's going to be 2 moles of aluminum produced. So those are a 1-to-1 ratio. And then from moles of aluminum, I can go to grams of aluminum. 1 mole of aluminum contains the molar mass of aluminum is 26.98, or rounds to 27.0. I can type that into my calculator, 150 divide 132. Now, you can times 2 divide 2. It'll cancel out. Times 27. And I end up with, I am going to produce approximately 28 grams of aluminum. So I'm going to produce around 28 grams of aluminum and 190 grams of calcium chloride. Now, depending on your rounding of atomic masses, you might have got 29 or something very, very close. As long as you round it appropriately and your numbers match your rounding, you'll be good. But just know that your numbers might be slightly off just depending on when you rounded here, but you should be really, really, really close. Now, these were 2 very, very fairly straightforward examples. A combustion, a single displacement. We're going to do one more practice problem today. So that we can start to tie back in, why in the world did we do density conversions? This time we are going to combine sodium hydroxide with sulfuric acid and produce a sodium salt and water. Balance the chemical equation. 1 sodium on the left. Oopsie, I miswrote that. That should be Na2SO4. 2 on the left, 2 on the right, so I need a 2 is my coefficient. 2 hydrogens, 2 hydrogens, 1 sulfate, 1 sulfate. Everything else is, I got 2 hydrogens here and 2 hydrogens here. So I need 4 hydrogens total. So I need a 2 out in front here. So 2, 1, 1, 2 to balance that chemical equation. And now we're going to start at a different place. We are going to say at the end of the reaction, .0 milliliters of water are collected. So now you're knowing what was collected at the end. And the density of water is equal to 1 gram per milliliter. So this is an easy density conversion, but it's still a density conversion. And I want us to calculate 2 things. What mass of NaOH was consumed, and what mass of H2SO4 was consumed. So now we're given a quantity at the back and we're going to calculate a quantity forward. I am going to start and just throw in, we should not need me to use video time to talk about how to calculate the atomic mass. The atomic mass of NaOH is 39.99, oopsie, that's a 9, grams per mole. And the atomic mass of H2SO4 is 98.07 grams per mole. So use those as your molar mass conversion factors. First step is NaOH. What mass of NaOH was consumed? Start with what we know. We know that 45 milliliters of water were collected. Now, milliliters is not on my mole conversion. I can go grams to moles to atoms. But using my density conversion, I can convert between milliliters of water and grams of water. My density is 1, so 1 milliliter contains 1 gram. From there, I can go and switch from grams of H2O to moles of H2O. And molar mass of water is 18. 1 mole of H2O contains 18 grams of H2O. I'm going to run out of room. From moles of H2O, I can go to moles of any substance. I'm going to NaOH. Two moles of H2O were used for every 2 moles of NaOH. And then from moles of NaOH, I can go to grams of NaOH. 1 mole of NaOH contains 39.99 grams of NaOH. Sorry, I ran out of room. Good lesson. As these problems get longer, probably need to use the whole page. 45 times 1 divide 1, divide by 18, times 2 divide 2, times 39.99. I produced 99, let me see, 45, 18. 0.975 grams of NaOH. Let me double check that one. So 45 divided by 18 times 39.99. Yep, I produced 99.98 grams of NaOH. I'm rounding to 3 sig figs. So that's actually, I'm going to put over here, 100 grams of NaOH produced. If these problems get messy, and they might, box in your work. Okay, last thing we're going to work through. What mass of H2SO4 was consumed? I'm going to start all the way over here now. Well, I started my reaction with 45 milliliters of water. Use my density conversion to go between milliliters and grams. From grams of H2O, I can go to moles of H2O using the molar mass. 1 mole contains 18 grams. From moles of H2O, now I'm going to H2SO4. I can go to moles of H2SO4. And from moles of H2SO4, I can go to grams of H2SO4. Now, mole to mole, that's a mole ratio. 2 moles of H2O are produced for every 1 mole of H2SO4 used. 1 mole of H2SO4 contains 98.07 grams of H2SO4. And again, that's just the molar mass that's from the periodic table. 45 divide 18 divide 2 times 98.07. I am going to make 122.5, or I'm going to use 123 grams of H2SO4. So there's your first kind of Stoich day, very similar to what we did in lessons 3, 4, 5, and 6. We're just adding in that conversion factor that allows us to convert between different elements in a reaction.